Hi, this is Koiro, and I was thinking about giving you a short update on the Schneider Euro PC. And a lot of viewers, and of course when we say a lot of viewers on this channel, it's about 10, has been giving me feedback and asking how this project is running. And I have to say, this is slow going. And that is not because we have not done any work on it, but it's done very little work that actually worth filming. Because what I've been doing is that I have been measuring from point to point on the board to see if there are some vias or some other traces that's broken or some other intermittent fault on the board. But here is a small update, and this will give you some lookout at what we have done, and also it will tell a bit about what we can do further on this computer. Yeah, as you might see, I have moved this motherboard into my desk inside my basement, and that's not because it's too cold to be out in the shed, but I do have some other projects running there. And what I'm doing now is that I'm actually connecting the plus and minus 12 volt to this board, and it's not because I do think it will do any difference, but I have had someone complaining that I did not connect them, and that they mean that that actually will make a difference. I don't think it will, but at least I have to try it. So I will try to inject this by making a lead that can connect this to my power supply, and the power supply I'm going to use is one that I made several years ago from a Cisco power brick that actually has both the plus 5 volt and minus 12 and plus 12 volt built into the same box. So that's what I will be doing here. I made this cable and I will solder this to the capacitors that stands as filter caps on the inside of the plus and minus 12 volt circuits. And from this schematics I think it's pretty clear that the plus and minus 12 volt only goes to the transistor output of the buffer drivers, the 1488 and 1489, that stands to the serial port and nothing else. Yeah, I will solder this to the ceramic caps, the C236 and 237, and I just measure out to see what's the earth side and what's the hot side of these capacitors. And the ceramic capacitors is easier to solder to than the electrolytic ones that has shorter leads. Hey, it might look a bit strange, but this is actually quite an easy way to do this. To make sure everything is right, I'm going to measure out all the voltages from the power supply, and the most observant of you have probably noticed that I've changed the blue and yellow color on the jacks that I put on the cable, so I have to take that into consideration. And I don't think it's a coincidence that all my coupling errors end up in Ukrainian greetings. It's now time to turn it on, and as you can see, we have lights in both the plus and minus 12 volts, but the reset line is still stuck on. And that of course tells us that the reset signal and to get the circuit spinning is our first priority. I have got some feedback that I didn't get the reset circuits right when I had my first walkthrough, and I try to simplify it here by collecting all the devices that actually is connected to some sort of reset signal and simplified the circuits so it should be obvious. And I do think I got it right, and I'm going to take a walkthrough now so that we are on board on how this works. And this is highly technical for someone, but I do think that everyone will learn something through this walkthrough. The reset signal starts up here in the corner with the 6805 chip, and this is the keyboard controller. And what we see here is that we have a circuit that's connected like this with a capacitor that is charging. And an open port is defined as a floating or high input normally on this kind of logic. And that means that this capacitor can charge through this port and reach a high level. And that will look something like so. If you have a diagram here with time this way and voltage this way. So it will charge like so, and at some point it will reach a high value, and then this will not be reset anymore. And that means that the keyboard controller is starting, and there is some kind of program in this keyboard controller that controls this port over here. And this is a programmable port, and it's tied to 5 volt normally. So when this device starts up, it's pulled towards 5 volt, probably an open collector output. And that means that this NPN transistor here is in the on state. And that means that this is pulled low. So that means that the reset signal that goes out here is pulled low at startup. And this is the same signal that connects all the way down here to the chipset. And this chipset also has a capacitor that keeps this stable when it's first put high. And this is the collector resistance that pulls up this circuit here. So this means that this actually is connected to the 5 volt through this 4K7 resistor and this 100K resistor. And that circuit pulls the circuit low until we get a low signal on PB4. Then this will be shut off and we will get a high signal in here. And a high signal will keep this from not resetting. We see this line over the reset. It means that this is an inverted input. It resets when it's low. Since this is an inverter from the start, this will get a low signal, and when we give a low in here, we will get a high here, and this is not resetting anymore. And this goes to the pin that's reset in down here, and as an output we have the reset signal here. And this reset signal, you can see it's connected 3 ways. It goes to the CPU reset up here that ties directly to the CPU, and this is the reset signal that we have been measuring on the CPU pin 21. If this is high, this CPU is resetting. But this signal also goes through this bus driver, the LS244 bus driver, and you can see this is always on. So this is just a transparent buffer because both these pins are pulled constantly to ground. So the S reset signal is always following the reset signal as long as this gate is working. So reset, a leak S reset, and you have the same down here. You have these signals also going down here to this one and to the B reset. And these are also pulled low, so this is just a transparent buffer. You can think of that as a wire straight to here. So you see out from this chipset FE2010A, we actually have 3 reset signals. We have the CPU reset, goes straight to the CPU, unbuffered. And we have the buffered S reset and B reset. And B reset, you can find that again as an input to the GIM chip. And as you might remember, the GIM chip is the chip that controls the glue logic for the Schneider parts with the joystick and so on. And it also controls some of the video circuitry down here. And this is probably to make the joysticks and other things fit to the screen and other things. I'm not sure why this is controlled from this one. And you can see that it also has a reset out pin here. And this goes to a second set of B reset. And B reset is bus reset. So this goes to some kind of bus. And let's take that one first. The B reset actually goes in to reset the hard drive. And this is the B reset that comes from here. It goes to this one. And it also goes to this one. And it goes to this one. And it goes to this one. And this additional bus reset here goes down to this one. So it helps reset the serial interface somehow. And this bus reset resets things that's normally on the ISA bus on the PC. The hard drive, as I mentioned, the parallel interface, and the floppy disk controller are all reset by this B reset here. And you also have another reset out from the GIM chip, and that is the V reset that you have here. And the V reset has two functions. It's connected directly to the Paradise PVC4 CGA chip. And that means that this won't start until the GIM chip has given OK. But there is one other purpose for this, and this is down here. And you can see that this is the output buffer for the CGA screen contact on the back of the computer. And that means that this controls the output. You can see here, this is the enable pins for this buffer. So if this signal is high, then there is no connection between the video output and the connector on the back. So this means that this V reset keeps the screen from showing garbled content until the Paradise chip and the GIM chip is ready. So every one of these actually fits together, and I of course forgot to take this up here. This B reset is of course the input here for the GIM chip. So everything starts up here with the keyboard controller. This is one, and then this is number 2, and of course the CPU starts as number 3, unbuffered to the core here. And you have these ones that goes to the bus reset. They are 4 together with this one, and you have the video output here as number 5. And this reset here, the S reset, this goes straight out to the port on the back. And this is the expansion slot, the ISA slot. And that means that the LED signal that we are seeing as a high on the diagnostic cards is actually connected to this one, like so. So if this buffer is broken, we won't get a reset signal out on the bus. And we have measured, of course, that the CPU reset and the S reset, that they follow each other, because we have tried to push this low and then the light turned off. So this might look like a dish of spaghetti with some ketchup on, but this is the way that this reset circuit actually works on this computer, and every reset available on the board is displayed here somewhat. So I do think I got the reset signals, and as you saw when we started this circuit, the reset signal was still high, and that means that we probably have some fault up here. There probably are some fault with the keyboard controller. And how can we remedy that? Yeah, we can. The simplest way is to tie this one. Oh, it's getting really garbled here, but if you tie this one to ground, like so, and the easiest way to do that is pull out this chip. So we take this out and we pull this one to ground. Then this will get a high input, and we get probably a low input through this FE2010A, and then we also can see that the reset is working through this. So that is what I'm going to try next. I'm going to pull the basis on the T3 transistor. I'm going to pull it low so that we force a reset signal through the keyboard controller. What you see here is me preparing for the schematic you actually saw in the last part here, because this is me checking out that I got the reset circuitry and everything surrounding the reset circuitry and the logic chip connected to it, that this was connected and that I had understood the schematic right. Because there always is some changes in the last minute, and there also are some errors in the schematics. So I was making sure that everything was all right. And I also take this as an opportunity to show you what I've been doing with this board since we last looked at it. I have been taking all the pins and measure that they have continuity to all the parts they should have continuity to in all the parts of the damaged board. And that means that I have taken the CPU, the FE2010, the keyboard controller, the EPROMs, the video chip and the buffer chips in the main part of the board and measure them out. I have not done the parallel serial, the GIM chip is not completely done, and I've not done the memory chips or the floppy controller chips. And it's a lot of work to make sure that you have continuity through every part of the board. And the sad part is that I have not found any bad trace on this board so far. Even all the vias in the damaged area seems to be working okay. But I'm going to test now with the oscilloscope to see if I have some waveforms. But before we can find any useful waveforms, we had to address this. This is the reset line stuck permanently high on the CPU. So we have to do something about that. And this is the reset line coming out of the keyboard controller, and this is stuck low to about 7.0 volt over the base emitter diode drop. And we have already discussed the solution for what we have to do now, and that is we have to bypass this reset circuit in this one, at least temporary, to see where that gets us. I'm just going to flip up this one. And just be careful, as this pins on this one is a bit corroded. Yeah, like so. And from the schematic of the 6805 microcontroller circuit, I do know that pin 1, pin 1 is ground, and I do have here, this is a 1 ohm resistor, just to use that to short this with. And I think the legs is going to fit in here, like so, and the reset is 489 is this one, I think. Yes, that is pin 29, like so. What we are doing here now is that we are sticking this low. So that means actually we're going to have a bit more power draw, because we have now one 4K7 resistor that is shorted to ground through this 1 ohm resistor. And yeah, I think it's safe just to turn this on. Yeah, and you can see at once here, you can see that the reset line, it did not light on. And we can check for clock. Was it this one? Yes. And we have 4.70 something megahertz clock signal, and that means that at least something around here has started. And this clock is supplied via this chip, and this chip is also the one that provides us with the correct reset signal, so that this signal now is low, has proved that at least some of the functions in this are working. And I can try to measure some of the pins on this CPU. I know that the clock was 19, but I know that the pins around here, this should be address pins. And I do have some activity now on the address lines. This was pin 2, and that is actually address line 14. Pin 3 is also some activity. Yeah, and I do have some more. So I do have some activity now on the address lines, and I can also try to see on the multiplexed data lines. That should be the lowest ones here. I know at least that I have something around here. This is 20, 19, 18, 17, 16. And here I also have some, and this is the latched, a bit more noisy output. But at least there is something trying to run on this CPU now, but I don't know what. Yeah, so what are we going to do? Yeah, I'm going to try to connect some screen capture device to see if there is some output on the screen. And this is not a video capturing device. This is a converter that converts from analog signals like VGA or composite or other types of video into HDMI. And the device is working quite nice, but it do have some issues, and one of the issues is that if I need to do some adjustment, it's a Chinese config menu on this. I connect this to my HP 17-inch monitor, and then it's just to turn it on and see what happens, and wait to see if we get any output on the screen. As you can see now, everything seems to be in the same state as it was last time. We might do some measurement with the scope just to check that everything is running like it did last time. Yeah, and we do have signals on these bus lines, so it should be running like last time. So it's coming to life the same as last time, but there is no output on the screen whatsoever, no sync, no nothing. And that we also probably can check with the scope. I do have the outputs here. Yeah, and they are all dead. And that means that this latch probably is looking. And that means that the next thing we have to do on this computer is to check the other reset signals. I have to check the video reset, and I have to check the bus reset to check that the other devices on this board is starting. We have established that the CPU is starting. It's trying to execute code. And we get nothing on the screen, so that means that a lot of the other circuits is not running. And maybe this temporary fix does not allow for any of the other chips to run, but I don't think that any other chip is dependent on this being here. But we might have to do some other botch wires inside here to get this running with this keyboard controller. And I mentioned this in the first episode, I think. This controller is not essential for this to run, because the actually keyboard logic for an AT or PS2 style keyboard is actually inside this chipset. So the data serial line and the data clock line is actually in this chip, and you can connect an AT style keyboard to this and bypass everything else that's on here. So that should not be the reason for this not working. So I do think that that's it for this episode. We do have to do some more work on this, but at least we are a bit further. We have got the CPU to run somewhat, and we do have a solid standing for what we need to do next. And that is, as I said, we have to sort out that the other reset lines actually are making the other chips able to run. And we have to check some other signals here, the RAS-CAS on the memory, to see if only ROM code is running or if it's trying to access memory. And we also have the circuits for the bus to the video chip. You have the video memory, and you have the video buffers up here. Maybe there is something wrong there. We do have to make a follow-up on that. So, thanks for watching. Hope to see you in my next episode. And please hit like and subscribe if you want to be notified when we post new videos. And I did learn a thing or two in this video, and I hope you did too. I always try to make the video so that there should be 1 or 2 learning points in each video. Hope to see you in the next one. Thanks for watching.